This conference will now be recorded.
Good morning, all. Today I'm going to give a demo on design for testability, which is DFT. So before we go into what is called as DFT, we will first try to understand what is VLSI design. So VLSI, it actually stands for Very Large Scale Integration. VLSI stands for Very Large Scale Integration. So VLSI means Very Large Scale Integration. So it actually means implementation of millions of transistors in a small area. So that is what is VLSI, implementation of millions of transistors in a small area. And the motive of VLSI or the goal of VLSI, you can call it. So if a particular company is designing a chip, then they will be having some primary goals or primary conditions that has to be met. That is what is the goal of VLSI or motive of VLSI. So the first one is high performance. Second one is low power. So we go for low power design in order to achieve longer battery life. Okay. So this is to achieve longer battery life. Longer battery life and low area. So we go for low area design because if our chip size is large, then our product size will be large. So that's why we go for low area design. Okay. So if chip size is large, chip size is large, then product size will be large. Product size will be large. Okay. So if our chip size is large, then the product size will be large. So that is why we will be going for low area design. And this is how our chip will look like after manufacturing. This is how our chip will be looking. Next, we'll go to ASIC. So ASIC means application specific integrated circuit. So which means the IC, the integrated circuit, which we are designing, it will be specific to a particular application. So for example, like if we are designing a modem chip, it can be used only as a modem chip. It cannot be used as a chip which is responsible for deployment of airbag in the automobile. Okay. So that is why the ASIC is application specific integrated circuit. The integrated circuit IC which we are designing, it will be specific to a particular application. If you are designing a modern chip, it cannot be used as a chip which is responsible for deployment of airbag in your automobile. Okay, it will be specific to a particular application. So ASIC flow means it gives the steps which we need to follow for designing a chip. So it actually gives the steps which is involved in the process of chip design. Okay. So first you have the design specification stage. So in the design specification stage, what will happen is based on the application for which we are designing the chip. So certain specifications will actually be decided, like what has to be the speed, how many memory modules are required, how many processors are required, how many sensors are required, what has to be the power. So such kind of specifications will be decided during the design specification stage. Okay. And after that, we have the design code stage. So design code stage, it will be like the design code of the chip will be written. It will be done by the design team. So they will be describing the functionality of the chip. Okay. So like they will be describing the functionality of the chip. So the design code of the chip will be written, and the code, it will be in behavioral and data flow level model. Behavioral and data flow level model. Okay. So this is actually done by the design team. So design team, they describe the functionality of the chip. They write the design code of the chip. So it will be in behavioral or data flow level model form. Okay. And then we have the verification team. So verification team, what do they do is they validate the functionality of the design in order to check whether it functions as intended or not. Okay. So that is what will be done by the verification team. So they validate the functionality of the design. They validate the functionality of the design in order to check whether like they validate the functionality of the design to ensure that it meets the required specifications and performs as intended. So that is what will be done by the verification. Okay, they will be validating the functionality of the design to ensure that it meets the required specifications and performs as intended. Okay, and after this, we will be having the synthesis team. So synthesis team, what will happen is this behavioral and data flow level model code, it will be converted into a structural form, or you can call it as a technology node specific gate level netlist. Okay, so the behavioral and data flow level model code, behavioral and data flow level model code, it will be converted into structural form. It will be converted into structural form, or you can even call it as technology node specific gate level netlist. Technology node specific gate level netlist. Gate level netlist. Okay. And after the synthesis team, we have the design for testability team. So design for testability team, we will be adding some test structures into the design during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip. So we will try to understand this in detail during the upcoming slides. Okay, we will discuss about this design for testing much more in detail in the upcoming slides. So basically, design for testability team, we actually insert some test structures into the design, like scan insertion, MDist insertion, boundary scan insertion, like that. We will be inserting some test structures into the design during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip. So we will discuss about design for testability team in detail in the upcoming slides. And after the DFT team, we will be having the physical design team. So physical design team, they actually convert the gate level netlist into layout form. So they convert gate level netlist, gate level design into layout form, into layout. So this is what is the physical design team. And after the physical design team, so after the physical design team, we will be having the sign off. So like in sign off, we will be taking care of in sign off, three things will happen. So one is the STA. So one is STA, and then next is physical verification PV and logical equivalence check LEC. Okay, so all these things where we can call it sign off. Okay, so here what is called as STA? So the full form of STA is static timing analysis. So static timing analysis, as its name suggests, it is a method of validating the timing performance of a design by checking all possible paths for timing violation. That is what is STA. Full form of STA is static timing analysis. As its name suggests, it is a method of validating the timing performance of a design by checking all possible paths for timing violations. And after that, we have the PV. PV is nothing but physical verification. So they verify the layout of the circuits. And then we have logical equivalence check. Logical equivalence check. So LEC is logical equivalence check. So LEC is actually done to check whether the final design is logically equivalent to the original design or not. So in order to check that, we'll be going for LEC. It is to check whether the final design is logically equivalent to the original design or not. So why we need to go for LEC is because, as you see, we had started with the chip design process with the design code stage where the behavioral and data flow level model form of the code was written. And at the time of synthesis, that behavioral and data flow level model form code, it got converted into structural form, or we can also call it as a technology node specific gate level netlist. So, and also if you're going for low power design, then certain special cells will also be inserted, like clock gating and then retention register, isolation cells, like that. Some more special cells will be inserted into your design. And then when we go for DFT, so we will be inserting our own test structures into the design, like scan insertion, MDist insertion, boundary scan insertion, like that. We will be inserting our own test structures into the design. And a physical design team, they will be converting that gate level netlist into layout form. So that is why if you see in each and every stage, if you see our design is undergoing a lot of changes. Okay, our design is undergoing lot of changes. Okay, so in each and every stage, what is happening is our design is undergoing a lot of changes. Okay, so that is why LEC is actually done in order to check whether the final form of the design is logically equivalent to the original design or not. Okay, whether the final design is logically equivalent to the original design or not. So in order to check that, we will be going for LEC. Okay, so actually LEC will be done after every stage, like after synthesis, after DFT, after PD. That LEC will be done after every stage. Okay, and next is we have the tape out. So tape out means delivering the database to the manufacturing unit. So that is what is tape out. And then finally we have packaging and testing. So this packaging and testing, it will be actually done after manufacturing. Okay. Packaging and testing, it is actually done after manufacturing. Okay. So packaging, so after manufacturing, this is how our chip will be looking like. So that big circle is the wafer and each individual portion will be the die. So covering this die with a protective layer will be called as packaging. And testing, it is actually done in order to check whether our chip is good or not, whether our chip has any manufacturing defects or not. So in order to check that, we will be going for testing. Okay. So in the upcoming slides, we will discuss more in detail about this design for testing and also regarding this testing much more in detail in the upcoming slides. So now we will try to understand what is DFT. So as I had told the definition in the previous slide, DFT is to insert test structures in the design. So we will be adding our own test structures in the design, like scan insertion, MBIST insertion, boundary scan insertion. Like that, we will be adding our own test structures in the design during the pre-silicon stage. Pre-silicon stage means before manufacturing. Okay. So pre-silicon stage means before manufacturing. Okay. To facilitate, to facilitate is to help in the detection of manufacturing defects in the chip. So if a particular chip fails after manufacturing, DFT team will be able to tell what manufacturing defect has caused the chip to fail. Okay. So if a particular chip, if a particular chip fails after manufacturing, DFT team will be able to tell what manufacturing defect has caused the chip to fail. Okay. So that is what is told here. So DFT is to add, is to insert test structures in the design. So we will be adding our own test structures into the design, like scan insertion, MBIST insertion, boundary scan insertion, like that. We will be adding our own test structures in the design. Sorry, during the pre-silicon stage. Pre-silicon stage is before manufacturing. Facilitate. To facilitate means to help. To help in the detection of manufacturing defects in the chip. So if a particular chip fails after manufacturing, DFT team will be able to tell what manufacturing defect has caused the chip to fail. Okay. And what is the role of DFT engineers? Role of DFT engineers, as I told, we will be adding some designs into the IC to make sure testing is done properly, as I had explained it in the previous slide. Okay. DFT engineers, they do not check the functionality of the chip. We rather check the quality of the chip. Okay, DFT engineers, we do not check the functionality of the chip. We rather check the quality of the chip. So let's try to understand this with the help of an example. So just consider a half adder design. So in a half adder, what is the expression for half adder? Sum will be A XOR B, carry will be AB. So whether this is written correctly or not, whether this is written correctly or not, that is what will be checked by the functional verification team. So in the ASIC flow, we had also seen about another team called as a verification team, right? So this is what. So the functional verification team, they will be checking the functionality. Okay, functional in the ASIC flow, we had seen another team called as a verification team, right? So that's what. So that functional verification team, they will check the functionality. Okay, so like for a half adder, if it is given as sum is equal to A XOR B, carry is equal to AB. Whether this is correct or not, whether this is correct or not, that is what will be checked by the functional verification team. They will be checking the functionality. So by mistake, if someone has written sum is equal to a plus b, carry is equal to ab. Suppose by mistake, if someone has written like this, then it will not function like a half adder. So this is what will be checked by the functional verification team. They will be checking the functionality. Okay. DFT team, what do we do? DFT team, we actually do not check the functionality. DFT team, we check whether each and every net of the half adder is free of defects or not. Okay, DFT team will check whether each and every net of this half adder is free of defects or not. So this is what is your intended design. So this A and B, it is actually coming from some flops. So both are XOR and that is what is your sum that is going to another flop. And then A and B again, it is coming from some flop. Both are ANDed, so that carry it is going to another flop. Okay, so this is what is your intended design. This is what is the intended design in this case. Okay. So suppose during manufacturing, say for example, this A net of this AND gate unintentionally got connected to ground. Okay, unintentionally during manufacturing, A net of this AND gate has got connected to ground. Okay, so this is what these kind of things only will be checked by the DFT engineer. Okay, so according to the intended design, the A input of this AND gate, it has to be coming from this particular flop's output. But unintentionally during manufacturing, A net of this AND gate has got connected to ground. Okay, A net of the AND gate has got connected to. So these kind of things only will be checked by the DFT team. So DFT team, we do not check the functionality. We check whether each and every net of this half adder is free of manufacturing defects or not. So this is what will be checked by the DFT engineer. We will discuss more in detail. Okay, we will discuss more in detail about the differences between the functional verification team and DFT team, and why do we need both the functional verification team as well as DFT team. We will try to see it in detail when we do a regular course. Okay. And what is testing? So we had already seen it in the ASIC flow, right? There was a step called packaging and testing. Okay. So as I explained there, this testing is actually done after manufacturing. So we'll try to understand what is this testing. So testing is a process of determining whether a device is good or not. So whether our chip is good or not, whether our chip has any manufacturing defects or not. Okay. So testing includes test pattern generation, application and output evaluation. Okay. So basically like these test patterns, it will be generated by the DFT engineers before manufacturing. Okay. Before manufacturing itself, DFT engineers will be generating these test patterns. So these test patterns, it will be consisting of input sequence and expected output. So these test patterns will be consisting of input sequence and expected output. So these test patterns, it will be applied onto the chip, and then the output of the chip, it will be compared with the expected output. So if output of the chip, if it is equal to the expected output, it means that the chip is passed. If output of the chip, if it is not equal to expected output, it means that the chip has failed. It means that there are some manufacturing defects in the chip. Okay. So what happens is these test patterns, it will be generated by the DFT engineers before manufacturing itself will be generating these test patterns. So these test patterns, it will be consisting of input sequence and expected output. So this input sequence, it will be applied onto the chip, and then the output of the chip, it will be compared with the expected output. Okay. So if the output of the chip, if it is equal to the expected output, it means that the chip has passed. If output of the chip, if it is equal to the expected output, it means that the chip has failed, which means that there are some manufacturing defects in the chip. Okay. So if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. So how we are able to give this detail? That we will be able to understand, that we will be explaining it like during our regular course. So once you complete the 3.5 months of DFT training, then you will be able to understand how DFT engineers are able to tell what manufacturing defect has caused the chip to fail. So this is what is regarding testing. And possible outcomes of testing, there are basically 4 possible outcomes of testing. Okay. So if a good IC, if it passes the test, it is nothing but true pass. Good IC means it has to pass the test only. So if a good IC, if it passes the test, then that is true pass. And if it is a defective IC means it has to fail the test. So if it is a defective IC means it has to fail the test. So if a defective IC, if it fails the test, then it is called as true reject. Okay. So if suppose A defective IC. If a defective IC, okay, if a defective IC, if it passes the test, defective IC, if it passes the test, then that is called as test escape. It is also called as under testing. Okay, if a defective IC, if it passes the test, it is called as test escape. It is also called as under testing. And a good IC, and a good IC, if it fails the test, if a good IC, okay, if a good IC, if it fails the test, it is called as yield loss. It is also called as over testing. Okay, good IC, if it fails the test, it is called as yield loss. It is also called as over testing. So goal of good testing will actually be to reduce the test escape and yield loss. Okay, and yield means number of good chips by total number of chips. So which means out of a total number of chips that has been manufactured, how many chips are good. So that is what is called as yield. Okay, number of good chips by total number of chips. Out of a total number of chips which is manufactured, how many chips are good. So that is what is yield. Okay. So manufacturing defects. So what are manufacturing defects? So manufacturing defects are nothing but the defects that are caused due to process variations and random imperfections. So process variation means slight variation in transistor channel length, metal interconnect width and thickness. So all those things can impact the logical and timing performance. Okay. And random imperfections means like unintentional shorts, unintentional opens. So they are called as the random imperfections. Okay. And what is the flow of DFT we will try to see. So flow of DFT, first we have the insertion. So insertion is adding extra logic. As I had already told, we will be adding some test structures into the design like scan insertion, embed insertion, boundary scan insertion. Like that we will be adding some test structures into the design. So that is what is called as adding extra logic. Okay. And then generation. Generation means we will be generating the test patterns. So the test patterns will be generated. So the test patterns, as I had explained in the previous slide, it will be containing input data and then expected output. Okay, so it will be containing input data and expected output. And then we have the validation. So we will be having the validation. So that validation will be done using simulation. Okay, we will be having the validation. So that validation will be done using simulation. So we will discuss about what are these things. We will try to understand these tips in detail in the upcoming slides as well. An overview about each of these tips. We will have an overview about it in the upcoming slides. Okay. So course outline. So what are the topics we will be covering in our courses? So first we will be covering scan insertion. Then we'll be covering scan compression. Scan compression is also called as EDT insertion. So we'll be doing that. And then on-chip clock controller OCC. Then automatic test pattern generation ATPG. Then simulations. Then JTAG joint test action group JTAG. So it's an IEEE 1149.1 standard. So this is a IEEE 1149.1 standard. And then we'll be having MBIST, memory built-in self-test, and boundary scan we will be having. We will also be covering IJTAG in our course curriculum. So IEEE 1687 standard. IJTAG also we will be covering it in our course curriculum. I have not included it in the demo session because in order to understand IJTAG, you first have to understand JTAG fully. So that's why I have not included it in the demo session. But we will also be covering about IJTAG 1687 standard, IEEE 1687 standard also in our course curriculum. Now, in the slides, I will just give you an overview about each step. So what is scan insertion? What is scan compression? Like that, I'll just give you an overview about each step. Okay. So first is scan insertion. So what is scan insertion? What happens during scan insertion is all the normal flops in the design. All the normal flops in the design. Okay. So all the normal flops in the design, they will be converted to a scan flop. They will be converted to a scan flop. And these scan flops, they will be stitched into scan chains. So this is what is scan insertion. So all the normal flops in the design, they will be converted to scan flops, and these scan flops, they will be stitched into a scan chain. Okay? So this is what is scan insertion. Okay. So in our regular course, when we do the course, we will explain like what is the scan flop, what is the functionality of the scan flop, what is the functionality of the scan chain, So all those things in detail, we will cover it during our regular course. Okay. So scan insertion means all the normal flops in the design will be converted to scan flops, and these scan flops, they will be stitched into a scan chain. Okay. So we will cover it during our course, like what is called as a scan flop, what is a scan chain, what is the functionality of a scan flop and scan chain. So those things we will cover it during our regular course. Okay. So why do we need to go for scan insertion? Why do we need to convert this normal flop to scan flop? And why do we need to why do we need to stitch the scan flop into a scan chain? So why do we need to do that? Okay. So we are actually going for scan insertion in order to gain controllability and observability of the design. Which means in order to easily control and observe our design, we will be going for scan insertion. Okay, in order to easily control and observe our design, we will be going for scan insertion. Okay, so that is what is the need of scan insertion. Let's try to understand with the help of an example. Okay, so say for example, I'm having a design. Okay, I'm having a design. So in my design, I'm having a 10-bit counter, a counter initialization circuit, and a counter observation circuit. Okay, I'm having my design. I'm having a 10-bit counter. So I'm also having a counter initialization circuit and a counter observation circuit. So suppose the counter is failing. So say for example, after counting 999, instead of counting 1000, it is again counting 999. So the counter is failing. Okay, so suppose if the counter is failing, so that is after counting 999, instead of counting 1000, it is again counting 999. Okay, try to see how many clock pulses will be required by the functional verification team and how many clock pulses will be required by the DFT team in order to find out that the counter is failing. Okay, how many clock pulses will be required by functional verification team and how many clock pulses will be required by DFT team in order to find out that this counter is failing. So let's try to understand. So functional verification team, as I had explained earlier, what do? They actually check the functionality. They actually check the functionality. So which means check the functionality means in this case, they will check whether the count properly counts from 0 to 1023. Okay, they will check whether the count properly counts from 0 to 1023. Okay, okay, checks whether the counter properly counts from 0 to 1023. Properly counts from 0 to 1023. Why? Because in this case, it is a 10-bit counter. In this example, I've considered a 10-bit counter. So that is why functional verification team, they will be checking the functionality. That is, they check whether the counter properly counts from 0 to 1023 or not. Okay. And then what is happening? Counter is failing at the 1000th pulse. In this case, counter, if you see, it is failing at the 1000th pulse. Counter is failing. Counter is failing at the 1000th pulse. Counter is failing at the 1000th pulse. Okay. Why counter is failing at the 1000th pulse? Because at the 1000th pulse only, the counter, instead of counting 1000, it is again counting 999. Okay. So counter is failing at the 1000th pulse. So in the 1000th pulse, why counter is failing at the 1000th pulse? Because at the 1000th pulse only, counter, instead of counting 1000, it is again counting 999. So counter is failing at the 1000th pulse. So for this itself, 1000 pulses are required. So 1000 pulses are required for this. 1000 pulses are required. Okay. And some more additional clock pulses will be required for counter initialization and counter observation. So additional clock pulses will be required for additional clock pulses for counter initialization, counter initialization, and counter observation. Counter observation. Okay. So some more additional clock pulses will be required for counter initialization. Counter initialization means the counter, it has to be brought to some initial state. Observation. Counter observation means the output of the counter, it has to be taken to some register and the register has to be read. Okay. So all the above, we can say that functional verification team, they require more 1000 clock pulses to tell that the counter is failing. Okay, why? Because functional verification team, they will check the functionality. So in this case, they will check whether the counter properly counts from 0 to 1023 because this is a 10-bit counter. So they will check whether the counter properly counts from 0 to 1023. So the counter is actually failing at the 1000 pulse. So 1000 pulses are required for this itself. So why the counter is failing at the 1000th pulse? Because at the 1000th pulse only the counter, instead of counting 1000, it is again counting 999. Okay, the counter, instead of counting 1000, it is again counting 999. Okay, so that's why counter is failing at the 1000. So 1000 pulses are required for this. And additional clock pulses, some more additional clock pulses will be required for counter initialization and counter observation. Okay, so ultimately we can say that the functional verification team, they require more than 1000 clock pulses to find out that the counter is failing. Okay, now coming to DFT team. So DFT team, we can approximately tell that the counter is failing. So we can tell that the counter is failing approximately in the range of 100 clock pulses. So range of 100 clock pulses means it can be somewhere around 80 or 90 or 100, 150 like that. Okay. So in the range of 100 clock pulses itself, DFT team are able to tell that the counter is failing. Whereas functional verification team, if you see, they require more than 1000 clock pulses. They require more than 1000 clock pulses to tell that the counter is failing. Whereas DFT team, we are able to tell that the counter is failing approximately in the range of 100 clock pulses itself. Approximately in the range of 100 pulses means 80, 90, 100, 150 like that. Okay. So how we are able to tell that? How DFT team is able to tell that the counter is failing in significantly less number of clock cycles? How? It is because we are going for scan insertion. We are going for scan insertion, so that's why we are easily able to control and observe our circuit. So that is what is the need of scan insertion. Okay, we are going for scan insertion, so that's when we are easily able to control and observe our circuit. Okay, so that is why DFT team is able to tell that the counter is failing in significantly less number of clock cycles. Okay, and how we are able to tell that the counter is failing approximately in the range of 100 clock pulses itself? So that, in order to understand this point, you first need to understand what is a scan cell, what is a scan chain, how a scan chain operates, all those things. So that's why this explanation of this point, we will give it during our course. When we do the scan insertion top, we will provide the information about this. We will provide the explanation about this point. Okay. And DFT team, we will also be able to tell what manufacturing defect has caused the counter to fail. Okay, DFT team, we will also be able to tell what manufacturing defect has caused the counter to fail. Okay, so like even this. So how we are able to tell what manufacturing defect has caused the counter to fail? Even this you will be able to understand once you complete the 3.5 months of the DFT advanced course. Okay, so yeah. Okay, functional verification team. Functional verification team, they can only tell that the counter is failing. Why? Because functional verification team, they will be checking the functionality. In this case, they will check whether the counter properly counts from 0 to 1023. So in this example, at the 1000th pulse, the counter, instead of counting 1000, it is once again counting 999. So that is why the counter is failing. So functional verification team, they can only tell that the counter is failing. Whereas DFT team, we will also be able to tell what manufacturing defect has caused the counter to fail. Okay, we will also be able to tell what manufacturing defect has caused the counter to fail. So how we are able to give this detail, that will be covered in the 3.5 months of your DFT advanced course. Okay, so this is what is the need of scan insertion. So scan insertion means we will be like replacing all the normal prop with scan flips, and we will be doing the scan chain stitching. And why we are doing the scan chain stitching? So that we can easily control and observe our circuit. Okay, as we are easily able to control and observe our circuit, we are able to tell that our counter is failing. In this example, we are able to tell that the counter is failing in significantly less number of clock cycles. Okay, and DFT team, we will also be able to tell what manufacturing defect has caused the counter to fail. Okay, so next is scan compression. So scan compression, it is also called as EDT insertion. So a single scan channel is internally divided into multiple scan chains, or you can even tell like the internal chains, they are compressed into external channels. Internal chains are compressed into external channels. So you can even tell like that. Okay, you can tell that. So this is nothing but your channel. This is nothing but your external channel. This is the external channel. So this external channel, it will be internally divided into multiple scan chains. So these are your internal chains. These are your internal chains. Okay. So your external channel, we can say that this external channel, it will be internally divided into multiple scan chains. We can say like that. But you can even say that these internal chains are compressed into external channels. These internal scan chains are compressed into external channels. You can say it. So this is what is called as scan compression. So these internal chains, they are compressed into external channels. Internal scan chains will be compressed into external channels. And why do we need to go for scan compression? So we need to go for scan compression in order to reduce the test time and also to reduce the test data volume. Test data volume is nothing but the number of bits of patterns. Okay, test data volume is the number of bits of patterns. So we will be going for scan compression in order to reduce the test time and also to reduce the test data volume. Okay. How if we go for scan compression, we are able to achieve reduction in test time and reduction in test data volume. How it is happening, that we will explain it during our course. So with the help of logically also we will explain, and we will also take with the help of formula. With the help of formula also we will show you that if you go for compression, then it will result in reduction in test time and reduction in test data volume. Okay, so we will cover it during our regular course. Okay, so in the regular course, we will show you logically also we will explain, and we will also explain with the help of formulas. We will also show you with the help of formulas that if you go for scan compression, we are able to achieve reduction in test time and reduction in test data volume. Okay, if you want to achieve scan compression, if you want to achieve scan compression, if you are using mental graphics design tools, then you need to add a logic called as EDT logic. So the full form of EDT is embedded deterministic test. Sorry. Full form of EDT is embedded deterministic test. So if you want to go for scan compression, if you are using mental graphics design tools, then you need to add up, then we will be adding up a logic called as EDT logic. The full form of EDT is embedded deterministic test. So this is what is the EDT logic, like what is it like? I have just kept only two components over here, decompressor and compressor components alone. I have kept it. Okay. So apart from this, you have some more components like the controller and then bypass logic. Like that, you will also be having two more extra components in this EDT logic. So we will explain about all these components. We will explain what is a decompressor, what is a compressor, what is a controller, what is a bypass logic, what role it plays, how we are able to achieve scan compression by inserting this logic. Those things we will explain it when we do the regular course. Okay, so this is what will be covered as a part of the scan compression topic. So scan compression means the internal scan chains, they will be compressed into external channels. And why we are compressing those internal scan chains to external channels, why we are going for scan compression, it is actually to reduce the test time and also to reduce the test data volume. Test data volume is the number of bits of patterns. Okay, so how if we go for scan compression, we are able to achieve reduction in test time and reduction in test data volume. We will explain it with the help of some formulas, and also we will also explain it we will explain with the help of formulas, and logically also we will show you that. Okay, if you want to achieve scan compression, if you are making use of metagraphics design tools, then you'll be adding up a logic called as EDT logic. The full form of EDT is embedded deterministic test. Okay, so there will be four components of EDT logic, two of which I have just shown in this picture. So one will be the decompressor, other will be the compressor. Then you have the controller and bypass logic, which I have not represented in this picture. So during the regular course, we will explain about each of these components and what role it plays during scan compression. And yeah, all those things we will be explaining it in, all those things we will be explaining it during our course. Okay. Next is automatic test pattern generation. Okay, automatic test pattern generation. So it is nothing but ATPG. So as its name suggests, it is a process of generating test patterns for a given fault model. So there will be various fault models like stuck at fault model, transient delay fault model, part delay fault model, IDDQ fault model. Like that, there will be various fault models. Okay. So ATPG means it is a process of generating test patterns for a given fault model. Okay. So during ATPG, what will happen is test patterns will be generated. And these test patterns will only be used to test the chip after manufacturing. So as I had explained it here, right, during this slide, I have already explained it. Okay. So while we were discussing about this testing slide, I have already explained it. So these test patterns, it will be generated by the DFT engineer before manufacturing. So it consists of input sequence and expected output rate. I had explained it in this slide. So the same thing is what is written here. Okay. So during ATPG, what will happen is during ATPG, test patterns will be generated. So these test patterns will be used to test the chip after manufacturing. So after manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. Okay. So during ATPG, what will happen? Test patterns will be generated. So these test patterns will only be used to test the chip after manufacturing. And these test patterns, it should be having a capability. What is the capability? After manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. And how are we sure? How are we sure that our test patterns will be able to detect most of the manufacturing defects? Okay, so how are we sure that our test patterns will be able to detect most of the manufacturing defects? So it is because our tool does fault simulation in order to generate the test patterns. Okay, so it is because our tool does fault simulation in order to generate the test patterns. Okay, our tool will be doing fault simulation in order to generate the test patterns. Okay, so okay. So what is this fault simulation process? What is fault modeling? What is fault simulation? How the ATPG tool generates patterns? What is coverage? What is coverage analysis and how to improve the coverage? All those things we will discuss it during our regular course. Okay, we will discuss all those things during our regular course. Okay, so ATPG is it is a process of generating test patterns for a given fault model. So during ATPG, test patterns will be generated. These test patterns only will be used to test the chip after manufacturing. So after manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. Okay, so our test patterns, they should be having the capability. What is the capability? After manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. And how are we sure? How are we sure that our test patterns will detect most of the manufacturing defects? It is because our tool does fault simulation in order to generate the test patterns. Okay, it is because our tool does a process called as fault simulation to generate the test pattern. So what is fault modeling? What is fault simulation? All those things, how ATPG tool generates patterns, all those things we will try to understand it during our regular course. Okay, what is a coverage? What is coverage analysis? What is coverage improvement? All these things we will cover it in our regular course. Okay, and next is simulation. So like simulation, it is actually to validate the patterns which was generated during ATPG. So which means before delivering the patterns generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that is what that validation is done using simulation. Okay. Before delivering the patterns generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that validation is actually done using simulation. So simulation is to validate the patterns which was generated during ATPG. Okay. And next is JTAG. JTAG is Joint Test Action Group. So it's a IEEE 1149.1 standard. So why do DFT team use JTAG? It is actually to minimize the number of ports from the top level and also to achieve boundary scan. Okay, in order to minimize the number of ports from the top level and also to achieve boundary scan, we will be making use of JTAG. Okay. So let me try to understand this point. So here if you see, I have kept a list of some important signals. Here I have kept a list of some important signals. So these are just some important signals. Okay, these are just some important signals. There will be many more signals like these. Okay, I have just kept a list of some important signals. So there will be many more signals like these. So if all these signals are to be controlled from the top level, that is if you allocate a top level port to control this int mode, allocate a top level port to control that Intel test enable, allocate a top level port to control that X mode. Same way for each and every signal, if you allocate a top level in order to control it, then what will happen? The number of ports from the top level, it will increase drastically. The number of top level ports, it will increase drastically. So that is why we will be making use of JTAG in order to internally control the static signals. Okay, we will be making use of JTAG to internally control the static signals. So that is why, if you see, we are minimizing the number of ports from the top level. Okay, so here I have kept a list of some important signals only. So there will be many signals like these. So if all these signals are to be controlled from the top level, that is, if you allocate a top level port to control each and every signal, then what will happen? The number of ports from the top level, it will increase drastically. So that is why we will be making use of JTAG in order to internally control these static signals. Okay, we will be making use of JTAG to internally control the static signals. So that is why we are able to minimize the number of ports from the top level. We are internally controlling the static signals, right? By using JTAG, we are internally controlling the static signals. So that is why we are minimizing the number of ports from the top level. We are able to minimize the number of ports from the top level. Okay. One is in order to achieve boundary scan. And yeah, this one also. How with the help of JTAG, we are able to internally control the static signals. How we are able to do it, we will be covering it during our course curriculum. Okay, the course curriculum, we will explain how with the help of JTAG, we are able to minimize the number of ports from the top level. Okay, so that we will cover it during our course curriculum. And next one is to achieve boundary scan. Next need of JTAG is to achieve boundary scan. So we will understand what is boundary scan is. Okay, so chip 1, chip 2, chip 3 are properly passing the test of DFT, but still the board is failing. Okay, so let's try to understand what it means. Okay, so like uh, after manufacturing, right? So first what will happen is chips will be manufactured. Okay, chips will be manufactured. Okay, chips will be manufactured. And then what will happen is chips will be tested on the tester or ATE. We call it as ATE. Chips will be tested on ATE. Okay, so uh, the full form of ATE is automatic test equipment. So it is also called as tester. So how it will be there is, this is only your ATE. Okay, so here the chips will be tested like this: chip 1, chip 2, chip 3, like this the chips will be there. So the input of the chip, it will be connected to the ATE, output of the chip, it will be going back again to the ATE like this. So this is how the chips will be tested on the ATE. So what will happen is, input sequence, it will be applied onto the chip, and then the output of the chip, it will be compared with the expected output. Okay, input sequence will be applied onto the chip, and then the output of the chip, it will be compared with the expected output. Okay, so like in this case, chip 1, chip 2, chip 3, they have passed their test. Chip 1, chip 2, chip 3, they have actually passed their test. They have passed their test. Okay, so which means they are not having any manufacturing defects. Not having any manufacturing defects. Manufacturing defects. So passed their test means, like as I had explained in the previous slides. So output of chip, it is equal to expected output. Output of chip is equal to the expected output. Okay. So now after this, what is happening? After this, the chips are placed on the PCB board. Okay, chips will be placed on the PCB board. Will be placed on PCB board. Okay, so this is how it will be there. This is your board, and this is how the chips will be placed. So chip 1, chip 2, chip 3. This is how the chips will be placed, and then the interconnection between the chips and all will actually be formed something. Okay. Next, what is happening? The board is tested. Board is tested. So board is tested. So at that time it is failing. So when the board is being tested, it is actually failing. When the board is being tested, it is failing. So why is the board failing? Because chip 1, chip 2, chip 3, they are internally not having any manufacturing defects because they have already passed the test on AT. So that is why chip 1, chip 2, chip 3, they are internally not having any manufacturing defects. Then why is the board failing? So this can be due to the manufacturing defects in the interconnection between the two chips. Okay, this can be due to the manufacturing defects in the interconnection between the two chips. interconnection between the two chips. So in order to test the interconnection between the two chips only, we will be going for boundary scan. Okay, boundary scan is actually to test the interconnection between the two chips. To test the interconnection between two chips. Okay, so that is why we go for boundary scan. So what is happening is chips will be manufactured. So chips will first be tested on the AT. AT is automatic test equipment. You can also call it as tester. So this is how the chips will be connected to the tester. The input of the chip, it will be the input sequence, it will be applied onto the chip, and then the output of the chip, it will be compared with the expected value. So in this example, chip 1, chip 2, chip 3, they have passed their test. So which means, as I explained in the previous slide, output of the chip is equal to the expected output, which means the chip 1, chip 2, chip 3, they are not having any manufacturing defects. Now what is happening? The chips will be placed on the PCB board, and then those interconnection between the chips and all are formed. Now when the board is tested, it is failing. Okay, when the board is being tested, it is failing. So why is it failing? Because chip 1, chip 2, chip 3, they have already passed their test on the ATE. So which means they are not having any manufacturing defect. They are internally not having any manufacturing defects. Then why is the board failing? It can be due to the manufacturing defects in the interconnection between the two chips. So in order to test the interconnection between the two chips only, we will be going for boundary scan. Okay. So this is what is boundary scan. How with the help of JTAG we are able to achieve boundary scan. So all those things, what is the structure of the boundary scan cell, all those things, like we will explain it when we do the course curriculum. Okay, when we do the regular course, we will explain that. Okay. And next is MBIST. So the full form of MBIST is memory built-in self-test. Okay. So we use MBIST technique in order to test the memory. As its name suggests, we will be making use of MBIST technique in order to test the memories. Okay. So why for memories we are going for separate MBIST technique? So why we are doing like that? All these things, what is an MBIST technique? All these things you will be able to understand it when we do our regular course. Okay. So full form of MBIST is memory built-in self-test. So as its name suggests, we use MBIST technique in order to test the memories. Okay. So this was regarding the theory part. And in labs, we will be covering all these things: IJ tag insertion, MBIST insertion, scan insertion. There are basically two approaches. One will be the top down and the other will be the hierarchical scan. So we'll be covering both the approaches: EDT and OCC insertion, ATPG pattern generation, ATPG and MBIST simulations. So all these things we will be covering it. And simulations also, we will be covering only no timing simulations. Okay, we will be covering only no timing simulations, because in order to do timing simulations, we require a file called as SDF file. Okay, we require a file called as SDF file, standard delay format file. So which is not available in our institute for the like it's not available for the test cases which is there in our institute. So that is why we will be going only for no timing simulations. We will be covering only no timing simulations. Okay. And boundary scan also, we will be covering it only theoretically, because we don't have the license for boundary scan. Okay, so these are the things which we'll be covering it in our labs. And in our labs, totally, our labs are structured into 4 levels. So level 1, level 2, level 3, and level 4. So level 1 projects, these are simple test cases. You'll be having a maximum flop count of around 100 flops you will be having. Okay, very simple test cases. Complexity will be very low for this level 1 and level 2 projects. So you will be having maximum of around 100 flops will be there in these 2 test cases. Okay, so we basically have 11 test cases in level 1 projects, for which we will be performing the scan insertions. In level 2 projects, for the same 11 test cases, we will be performing scan compression, which is EDT insertion, then ATPG and simulation. For the same 11 test cases, we will be performing that. Level 3 and level 4 projects, they are designs with higher complexities. Like in level 3 projects, you will be having around 4K flops, and in level 4 projects, you will be having around 44K flops. So level 3 and level 4 projects, they are actually designs with higher complexities. Okay, they are actually designs with higher complexities. So you can actually mention this level 3 and level 4 projects as a project work in your resume. Okay. So in level 3 projects, we will be doing the hierarchical scan, and in level 4 projects, we'll be doing the top-down approach. Okay. Level 4 projects, we cover everything like IJ tag and embed insertion. Okay, we'll be covering everything. IJ tag and embed insertion, IJ tag and embed insertion, and then EDT and OCC insertion, EDT, OCC insertion, synthesis, scan, ATPG, simulation. So everything we will be covering. Okay, so if you see in the level 1 and level 2 projects, we did not do this IJ tag embed and then this OCC insertion and all, we have not done it. But in level 3 and level 4 projects, we will be covering everything. So IJ tag and embed insertion, EDT, OCC insertion, synthesis, scan, ATPG, simulation, everything we will be covering it. Level 3 projects, it will be hierarchical scan approach, and level 4 projects will be a top-down approach. Okay, so this is what we will be doing. And tools used for DFT. So for performing DFT, you'll be having all these tools. So as synopsis, cadence, and mentor graphics tools are used. So in our course, we are going to make use of this mentor graphics tools. So for MBIS, we are going to make use of this Tessent MBIS. For scan, we are going to make use of the Tessent scan. For scan compression, we are going to make use of this Tessent test compress. For ATPG also, we are going to make use of this Tessent test compress. Simulations, we are going to make use of this Questa sim. So at one stage we have to perform synthesis. So for synthesis alone, we will be making use of the synopsis tool, which is the design compiler. Okay. So at one point we'll be performing the synthesis. So for synthesis alone, we will be making use of the synopsis tool, which is nothing but the design compiler. Okay. And who can attend this course? So if you are a student in any final semester of your college, if you want DFT as your course curriculum, then you can if you're having DFT as your course curriculum, you can enroll for this course. Or else a new college graduate, so who is from relevant branches of engineering and science. So say for example, you are from ECE or E&I, so those departments if you are there. So if you want to get selected in some VLSI company, then you can enroll for this course. Okay. Lecturers or professors who want to switch their career into real-time industry experience. So if you're like an electronics professor or an VLSI professor, and if you want to switch to real-time projects, real-time industry experience, you can attend this course. And even working professionals from similar or other VLSI domains. So say for example, you're there in IT field and you want to switch your domain to VLSI field. If you want to switch your domain, you can attend this course. Or else in VLSI itself, say for example, you are a physical design engineer, but now you want to gain some experience in DFT side. Then if you want to switch to DFT side, you can also attend this course. Okay. So, and then placement support. So we are actually having tie-up with various VLSI companies. So you'll be eligible for attending the interviews based on your performance in course assignment, and we will also be conducting some mock interviews, tests, presentation session. So all those things will be there. So based on your performance in all these things, you will be added into a group called as a job support group. So in that job support group, the placement opportunities will be posted. Okay. And during our course, we will also be conducting some mock interviews, and previous interview questions and preparations we will be giving. So previous batch students, they would have attended some companies, right? Interview questions they would have attended. So those interview questions also we will provide you the training. And yeah, that's it for the demo. If you have any questions or queries, you can post it in the chat box. So basically, like this course you will be, this is actually a total of 6 months course. So total 6 months course will be there. So out of which 2 months will be basics. 2 months will be basics. All these topics will be covered, like digital design, Linux, CMOS, then Verilog, um, all these things will be covered uh, during and then GWIM, all these trainings will be given. So these are the basic training. Okay, so in the basic portion, all these things you'll be given training on all these things, and the next 3 to 3.5 months, next 3 to 3.5 months. So we will be having the DFT advanced course. DFT advanced course will be there. So that is what I have discussed now. So what are all the topics will be covered in the DFT advanced course, and what are all the labs and theory portions will be there in the next 3 to 3.5 months course. So that is what I have described it here. That is what I have given in my demo class. Uh, like, uh, can you check with Srinivasa sir about it? So sir will be able to give you a good guidance whether like computer science students can also enroll this subject. Okay. So sir will be able to provide you a good guidance on that. Anybody else has any other questions related to the course? So the course schedule, all those things like course schedule, all these things, it will be posted to you in your DFT groups. It will be posted. Okay. So uh, when the sessions will be starting, what is the session for that week, everything will be posted in your DFT groups. Triple E, I think you can attend it, but like you can also once get the confirmation from Srinivasa sir. So uh, sir will be able to give you good guidance on that. Okay. So ECE and E&I students for sure you can attend it. So other domains like you can once get confirmation from Srinivasa sir. So sir will be able to give you good guidance on that. Any other questions do you have regarding the course? Class timings, like it will be differing from one batch to the other batch. So that will be posted in your DFT group. So you will all be you will be put into a DFT group. You will be a part of a DFT group. So the weekly schedule for that particular batch, it will be posted in the DFT group. Okay. And you will also be having an individual group which is created with your VLSI Guru ID and your name. So you can also message in that individual group. So Bhargavi ma'am will be able to address queries regarding class timings. Okay, because it will be different for each batch. Uh, Okay. So what is a flop? So all those things it will be covered during digital design part of the training. So that is what is your question, right? Basic terminology will be explained related to topic like flop. Yes. So like regarding various flops, what are the flops? Like combinational logic, sequential logic, all those kind of things. It will be covered during the digital design part of the training, which will be happening in the first 2 months. So first 2 months you'll be having the basic training. So at that time, during the digital design part of the training, all these things will be covered about the basic combinational and sequential logic. Uh, I will just, Narayana, I'll just share Manoj sir's number. So, sir is from placement department. So, if you can, once check with Manoj sir, so he will be able to guide you regarding the requirements of the companies. Okay. So, I'll just post his number here. You can check whether 6.8 CGP also will be allowed to attend the placements. Okay. So, let me just share with you his number. One second. So, this is Manoj sir's number. So I've shared Manoj sir's number. So sir is from placement domain. Sir will be handling the placement related placement related tasks. So if you just check with that sir, he will let you know whether what is the company's requirement, whether they are like whether if you have a CGPA of 6.8, whether you'll be able to like allowed to attend the interview or not. So sir will be able to provide you the guidance. If an individual group is created for you, so with your VLSI Guru ID and your name, if an individual group is created, then you can like post in that group itself. So in that group, all the faculty will be there. So the respective faculty will address your doubts. So if you have an individual group which is created, you can directly post it in your individual group. Anything else regarding the DFT course? If you have any doubts, you can ask. So I've just seen the I just saw a few companies in the job support group regarding their requirements. So few companies are only specifically asking for 70% and above percentage. So other companies they have not specified any such criteria. So I think you can attend it. You'll be able to attend those companies. You can even like get confirmation from Manoj sir as well. So sir will be dealing directly with companies, so he will be able to give you good guidance on that. Okay. As far as I've seen in the requirements, what the companies have posted, only few companies they are specifying the percentage required percentage they are specifying. Others they have not posted any requirement like that. Okay, so I think you'll be able to attend the placement for those companies. But once you can get the confirmation from Manoj sir as well. So he's from placement department, so he will be able to give you good guidance on that. Yes, Naveen, you can. Yes, Navadeep, you can leave the meeting. Duration of session. Um, Gate score, it is actually not required. Okay, gate score is not required for this. And duration of session, usually like a theory session, it will be for 3 hours. So theory session will be for 3 hours. Theory sessions, it will be for 3 hours. And then lab sessions, it will be for 2 or 2.5 or sometimes even 3 hours. It depends on what kind of test case we are doing. Okay. So yeah, this is how the duration of session will be. The theory session will be 3 hours. Lab session either sometimes it can be 2 or sometimes it can be 2.5, sometimes it can be even 3. It depends on the test case which we are doing on that current day. Okay. And then after 6 months course, there will be any preparation sessions or classes regarding interviews or revision. So during the 6 months course itself, we will be covering those interview question and discussions, all those things we will be doing it during that 6 months course itself, during that 6 months course time itself. We will also be including those in previous company interview questions and discussions. Okay. during the sessions, during that 6 months course session itself, we'll be including that as well. So after the course completion, you'll be given mock interviews. Mock interviews will be conducted for you. So based on your performance, you will be added into a job support group. So where the placement opportunities will be posted. So if in case your mock interview score is not good, then you will be given some more time to prepare, and then you will be again given a chance to attend the mock interview. And regarding revision sessions or interview preparation sessions, if you request it, and there will be an individual group which is conducted, individual group which will be created for you. So if you want further assistance, like further placement support, or further revision sessions like that, if you want some more extra support, if you want, you can request that in the individual group. So once you enroll in the course, group will be created with your VLSI Guru ID and name. So you can post it in that group. So based on your requirement, extra sessions will also be conducted. Okay. Um, Last one in the basic course, the GVim editor. Okay. So the GVim editor, text editor. So that is what will become. That is what I had mentioned there. Yes, offline classes also will be there. So you can check that also with Bhargavi ma'am. I will share with you her number. Either Bhargavi ma'am or Usha ma'am, you can just contact. I'll share with you their numbers. One second. One second. So this is Bhargavi ma'am's number. And I'll also share Usha ma'am's number. You can once confirm it with them as well. I forwarded their number. Regarding the course schedule, so whether it will be an offline class or online class, or what will be the schedule for your batch. So all those things, you can either contact Bhargavi ma'am or you can contact Usha ma'am. So they will be guiding you on that. So any other queries you have? Okay, then thank you all. We can end today's class. What's the validation time for the tools for students if required? You're asking like okay. Uh, for beyond course, if you want to extend the tool access, so how much extra time they can provide, right? Okay. So I'll share Manohar sir's number. So he will be able to. You can check with that sir. So he will let you know. I'll share with you his number. 16. Okay. So I have shared Manohar sir's number. So he will only be providing those tool access, all those things. So like you can just check with that sir. So he will be able to guide you on this question. So if you have an individual group which is formed, you can directly post it in that individual group itself. So directly you can post it in that individual group. All the faculty will be there. So they will be addressing, like respective faculty, they will be addressing your doubts. If the individual group is not created, then you can contact them in the individual numbers. So yeah, thank you all. We will end today's class.